All right. Hello, everyone, and welcome to the Compass Seminar Series. Today, I am very excited to introduce Dr. Sujan Shrestha. He received his bachelor's degree in environmental engineering from Kathmandu University, Nepal in 2015, after which he spent 2.5 years working as a research consultant at the International Center for Integrated Mountain Development. He recently completed his PhD at Baylor University, studying anthropogenic and biogenic VOCs in urban and remote locations under the guidance of Professor Sheasley. Currently, he is working in possibly the best research group, which is the Gaston Lab, as a postdoctoral researcher studying Saharan dust particles at the Barbados Atmospheric Chemistry Observatory, aka BACO. Outside of the lab, Sujan enjoys spending time in the Rosenstiel School gym and occasionally playing soccer and or volleyball. With that, if everyone could please give Dr. Sujan Shrestha a warm welcome.
Thank you, James, and thank you everyone for joining me here today. So today I'll be talking about some insights into urban air quality with the perspective of biomass burning plume and ozone formation chemistry in Texas cities. So this talk is a part of my PhD dissertation. So that's why it's in Texas. And as my new project in Erasmus is just starting up, so maybe something on it in future seminars. So anyways, to begin with, what is air pollution and why do we care about it? Any unwanted substances in the atmosphere are harmful substances. That's the pollutants. And why do we care about it? Is because we're breathing the same air, and that's harmful to human health, right? Additionally, these pollutants also have effects on climate. So majorly there are two components of atmospheric pollution. First is the gases, some of which are some of the potent greenhouse gases like carbon dioxide, methane, as well as some of the gases that are found in trace elements in atmosphere like carbon monoxide, ozone, nitrogen oxides, and sulfur dioxides. Apart from that, there are also volatile organic compounds, or VOCs, some of which are like benzene and toluene. And the second component is aerosols, which includes inorganics like sulfates, nitrate, ammoniums, as well as several organic carbons and elemental carbon. Once these pollutants are emitted into the atmosphere through natural and anthropogenic processes, they undergo chemical reactions or chain of chemical reactions forming secondary pollutants. Because my talk today here will mostly focus on VOCs and aerosols, so I'll briefly introduce that. So the term VOC, it refers to all carbon-containing gas phase compounds except carbon dioxide, carbon monoxide, some carbonic acids, and ammonium carbonates. A large variety of VOCs have been detected in the atmosphere. And these VOCs are released to natural and anthropogenic processes. So the Earth's vegetation naturally emits biogenic VOCs, whereas some of the primary sources of anthropogenic VOCs are traffic emissions or industrial plumes, as well as biomass burning. But I want to make a note here that biomass burning can also be from natural sources. For example, lightning-induced wildfires, right? In this figure here, what I show is the global estimate of total VOC release from some of the major sources. And the numbers that I put here for the VOC release from these sources are highly variable between emission inventory and model outputs. Apart from that, why do we care about VOCs? It's because these VOCs in an urban or suburban region where there's some amount of NOx, whether low or high, these can undergo photochemical reaction forming ozone as well as secondary organic aerosols, and both ozone and secondary organic aerosols or SOAs are harmful to human health and ecosystem. Apart from that, even the individual VOCs can be harmful to human health, like for example benzene. And the other thing to notice is that all VOCs may not have equal contribution to ozone formation or SOA formation. So it largely depends upon the intrinsic reactivity of individual VOC as well as its abundance in the atmosphere. Therefore, characterization of sources and chemistry of VOCs in urban areas, it is important in terms of ozone chemistry. Now coming to atmospheric aerosols, aerosols are suspended particles and liquid droplets in the atmosphere, which plays an important role in regional air quality and climate. So effects on air quality is straightforward. You have increased particulate pollution. That means the air quality is poor, and that can affect human health. Whereas in terms of climate, it can affect directly and indirectly. So the direct effect is aerosols absorbing and scattering the incoming solar radiation, thereby altering Earth's radiative budget. Whereas the indirect effect is aerosols serving as a cloud condensation nuclei, or CCN, for fog and cloud formation. So if you have more CCN, that leads to more cloud droplet number, and therefore it can change the precipitation cycle. But these direct and indirect effects, they largely depend on aerosol composition, shape, and size. Although we are in Florida right now, but because my talk today will be mostly focused on Texas cities, so I'll briefly talk about how is the air quality in Texas. So Texas, being one of the largest state in the United States, has several metropolitan areas like Dallas, Houston, El Paso, San Antonio, right? And in these metropolitan areas, there's a large number of refineries, manufacturing industries, oil and gas extraction processes going on. So these sources emit a lot of amount of pollutants into the atmosphere. Therefore, the state of Texas, through Texas Commission on Environmental Quality, like any other state, they have several monitoring stations measuring some of these PM concentrations, ozone and VOC concentrations. So in this figure, what we see is the trend of PM and gases over the last 2 decades. And what we observe is, with the implementation of greener technologies and stricter policies, the concentrations have decreased over time. But if you see, starting from 2017 or 2018, there has not been a significant improvement any further. And then the other thing is, there are still several Texas cities that exceeds the US national ambient air quality standards for ozone and PM. With all the data that the state agency gathers, it brings it together, lump it, and run some source apportionment models and calculate the state-wise averages for different sources. But the thing is, these state-wise averages have high uncertainty, because any pollutants, whether VOC or other particulate pollutants, they have large spatial variability as well as temporal variability. Therefore, VOC and other emission characterization needs more spatial and temporal coverage. Besides these primary sources, there are episodic transported biomass burning plumes and dusts that also impact Texas air quality. For example, in this figure here, we can see the spatial distribution of aerosol index, which is the proxy for the amount of aerosol in the atmospheric column. So in the first figure A, what we see is there's a development of high aerosol index in Canadian Alaskan border, as well as in the northwestern US. This was due to the ongoing forest fire, which increased over time, and the plume then later traversed to southern Texas, impacting air quality in Houston area. This transport even caused the ozone to exacerbate above 125 ppbs, which was the highest recorded ozone between the year 2001 and 2005 in entire Texas. So this is one of the several instances that impacts the Texas air quality through the transported events. These introduction slides that brings to two objectives that I'm going to talk about today. The first one is to study the ambient concentration and identify sources of ozone precursors like VOC and gases in Texas cities. I'll be showing some results from my field campaign in San Antonio and Houston. And my second objective that I'll be talking about is using VOC measurements and aerosol optical and chemical measurements to identify impact of long-range transport of biomass burning plume in an urban location in Texas. And I'll be showing some results from Port Aransas, which is a coastal city near Corpus Christi, again in Texas. So For those who doesn't know the layout about Texas, this is the zoom-in view of the southeastern Texas, and I had sites in Houston, San Antonio, and Port Aransas, and these colored paths are the mobile measurement paths that we had covered during one of the field campaigns. Whereas in terms of methods, for VOC measurements, I had used PTRMS, which is proton transfer reaction mass spectrometer that can measure a suite of different VOCs, including anthropogenic VOCs, biogenic VOCs, and secondary oxidation VOCs. I won't go much detail about the instrumentation though in here today. But in terms of aerosols, the first measurement we had was the aerosol optical measurements of aerosol scattering and absorption coefficients. And these direct measurements of aerosol absorption and scattering coefficients were then used to calculate some of the intrinsic aerosol optical properties. These intrinsic aerosol properties are usually helpful to characterize sources and composition of the aerosols. The first one that I had calculated was the absorption angstrom exponent, AAE. The second was scattering angstrom exponent, SAE, and the third was single scattering albedo, SSA. Usually AAE and SAE provides information about the wavelength dependency of absorption and scattering. For example, black carbon, the soot that's emitted during fossil fuel combustion, that has very weak wavelength dependency and absorbs equally throughout the UV visible spectrum. Therefore, the AA value is around 1. Whereas biomass burning emits black carbon, and on top of that, it also emits the observing organics called brown carbon. So this brown carbon has very strong wavelength dependency in the lower UV visible spectrum. That's why when we calculate A for brown carbon dominated air mass, we get the A value above 1, and depending upon the composition of the chromophores of brown carbon, it can be 2, 3, or even higher. Whereas SAE, or the scattering angstrom exponent, is inversely related to the particle size. So if you have larger particle dominated aerosol, for example dust evens, then your SAE is lower, less than 0.5 or even sometimes less than 0. Whereas if you have finer particles, SAE above is higher than that. And the third parameter is single scattering albedo. SSA provides the information about the observing or scattering nature of sampled aerosol. For example, if SSA is greater than 0.95, it basically represents a high contribution of scattering aerosol, causing net cooling effect. And if it's lower than 0.9 or so, it means there's a observing dominant aerosol in the sampled air. Apart from these VOC and aerosol optical measurements, I also had supporting measurements of trace gases like CO, NOx, carbon dioxide, and ozone. And I also had very important measurements of methane and ethane. In terms of aerosol speciation and some size distribution, I had high resolution time of flight mass spectrometer, which is very appreciated instrument in our aerosol field. And we had some meteorological data to cover some of the air mass questions. Apart from that, I had used some satellite and models based on NASA and NOAA. So coming to the first topic, where I wanted to understand the VOC concentrations and sources in a major urban area in Texas, San Antonio as my study site. So why San Antonio? Because San Antonio is a growing city in the US, which has population growth rate of around 17%, which is ranked second nationally. And because of that, it has resulted in the development or the increase in the economic activities in terms of transportation and service sectors. So these sectors have caused increase in pollution. These developments have caused increase in pollution in San Antonio. So until 2015, San Antonio met the US National Ambient Air Quality Standard for ozone, so there was no questions. But after that, later after 2015, it could not meet and was designated as marginal non-attainment for ozone pollution. And this was the first study in San Antonio to comprehensively understand VOC chemistry. In terms of sampling sites, so during the San Antonio Field Study 2017 field campaign, or SAPS 2017, we had two sites. First site was at Travelers World, which is urban downtown site, whereas we had our second site up in the southeast direction from the urban location at University of Texas at San Antonio campus, which is suburban site, and we had our 2 mobile labs stationed on individual sites with similar instrumentation. In terms of the specific goal of the project, we wanted to understand some sources and temporal variability between the urban and suburban site, and we wanted to compare the contribution of local and aged air mass between the 2 sites using gases measurements. And the third objective was to analyze the source and meteorological condition which led to high ozone days during the campaign. Today I won't talk much about the first and a part of the second objective, but just summarizing, we saw some interesting geospatial differences between urban and suburban location, and we showed some comparison about the ambient concentrations or average concentration of different VOCs. But moving on to ethane and methane study of oil and natural gas sources during the campaign. So usually what happens is emission of methane is identified based on the co-emission of ethane using this ethane to methane enhancement ratio, and different field previous literatures and field measurements have given a ratio relating to individual kind of industrial processes. For example, oil extraction process, which is wet gas, has the ratio of about 6%, whereas the natural gas extraction process has other industries in and around those locations. Those processes cause the methane and ethane ratio to be around 1 to 6%, and some biogenic sources like landfills and agriculture fields emit they do not emit ethane so much. That's why the ethane to methane ratio is around 0%. So within this high scatter of ethane to methane ratio, what we see is a few distinct trend lines that were evident during the campaign. For example, the May 14th and 15th in the reddish dot have a distinct methane to methane ratio of 7%, which relates to the atmosphere at that time being dominated or influenced by the wet gas or natural gas, the oil extraction process. Whereas there were several days like May 13th, 21st, and 24th where we had influence of the natural gas extraction processes. So why this is interesting is because if we compare to similar result from another big city in the US, Boston. So this study had compiled year-long methane and ethane measurement from 4 different sites, but what they see is like a dominance of one single kind of oil and gas extraction processes, which was not the same as what we saw in San Antonio. Now coming to the high ozone days that we had identified in the campaign. So during the campaign, we identified 3 high ozone days in May 17, 13, and 14, where the ozone peaked above 17 parts per billion. And I'll be showing some results about it, but we also have, to compare some results, I have 3 low ozone days, which are marked in this blue arrows. These days had ozone less than 50 ppbs, but there were days which had lower ozone than this, but we wanted to use a day which had high actinic flux, meaning the day was photochemically active but didn't produce as much ozone. Now, to better understand the atmospheric composition and meteorological condition that led to high ozone days, I put the VOCs trace gas data for May 13 and 14 as well as a day before that in a composite plot here. So what we see is that we observed higher concentration of ozone precursors like trace gases, NOx, CO, as well as VOCs the night preceding the event day. So the interesting thing was the average VOC concentration on the night before was above 90th percentile of the campaign average. So during when we have a shallow boundary layer at nighttime and when we accumulate so much of the ozone precursors, this can then favor ozone generation on the next day. And the second thing is when I looked into the backward trajectory of where the air mass is originated from. So what we observed was, although during the entire campaign, the most dominating source was southeastern wind, but on these days when we had high ozone, the air mass changed from southeast to the northwest direction. And when I compare low ozone days, background ozone concentration between low ozone days and high ozone days, what we saw was the regional background was above 30% on the high ozone days compared to low ozone days. Why this kind of analysis is important? Because usually the government agencies or the state agencies, they want to characterize similar kind of meteorological and source condition that leads to high ozone days in order to formulate the target management strategies. Now coming to the comparison between anthropogenic VOCs between San Antonio and Houston. So these slides will come off of a separate field campaign than what I showed earlier. So during the year 2021, we went back to the same urban site in San Antonio, which is urban location closer to the downtown San Antonio. During the field campaign Corpus Christi and San Antonio Field Study 2021, and we went to Houston after a couple of months in the same year during a Tracer AQ field campaign. And at Houston, our site was located in San Jacinto Battleground, which is situated on the Houston shipping channel, closer to a lot of different kind of industries like petrochemical, refineries, manufacturing, as well as the intersection highways. And the specific goals of this project was to use trends and emission ratios to characterize sources of VOCs in these two cities. We also wanted to compare the observed sources of VOCs from our measurements with the emission inventory data. And then we wanted to analyze the ozone production sensitivity, whether ozone production was dominated by VOC chemistry or the NOx chemistry. So in this figure, I put the ratio of daytime to nighttime average for benzene, toluene, and xylene, which are commonly considered as anthropogenic VOC, isoprene and MEK, which are daytime biogenic VOCs, generally considered, and then CO, which is a general combustion tracer. So, and I have put a dashed line at 1 so that it's easily visible what time of the day had higher contribution or lower contribution. What we observed is that in San Antonio, the BTEX or CO had minimal difference between day to night, and isoprene and MEK were elevated during the daytime. This is like common kind of pattern you see in major urban areas in US, where anthropogenic VOCs are dominated by traffic emissions, and the biogenic VOCs or isoprene and MEKs, these kind of VOCs show daytime photochemistry. However, Houston had a very different day versus night average, where not only benzene, toluene, and xylene had day versus night ratio less than 1, but also MEK. And interestingly, the isoprene was lower than 1. The ratio of daytime versus nighttime for isoprene was less than 1. So what this implies is there's a lot of industrial sources that were emitting these VOCs intermittently in high concentrations at nighttime. Therefore, in order to achieve a more thorough, comprehensive analysis of the difference between day versus night emissions, in these figures, I show BTEX and isoprene MEKs at San Antonio, the top 2 plots, and Houston, the bottom 2 plots. Night times are patched in gray. The first thing that we notice is the difference in the scale of the peak emissions. So there's a stark difference between peak emissions between the two sites. And the second thing is, as we had assumed, if you see some of these peaks at nighttime for isoprene or MEKs which comes along with benzene and toluene, So these can't be biogenic, right? So these were potentially dominated from the or emitted from the industrial, came off of the industrial emissions. Now we wanted to compare the sources that we observed from our measurement with the emission inventory data. So the first figure A has the fugitive and stack emissions within the 10-kilometer radius of our study site. That's documented in the state emission inventory data. And what we see is there's a stark difference. If we compare the axes, range of axes, then there's a large difference between the total VOCs that's released from these fugitive and stack emissions or industrial emissions between the two sites, whereas the emission inventory for on-road mobile sources or traffic emission, Houston only has 2 times more VOC release from traffic emission compared to San Antonio, and this also corroborates the fact that in the Houston shipping channel area where we were in Houston, that location had high contributions from industrial emissions. Now coming to the ozone production regime between the two cities. So the OPE or the regression-based OPE that I have shown here is one of the several ways to calculate or determine ozone generation as a function of NOx elimination from the system. And what we see is that in Houston, so okay, in this plot, the OX versus NOG plot, if the slope is less than 7, that means it's VOC limited or VOC sensitive ozone production, and if it's greater than 7, it indicates NOx sensitive ozone production. What we see is that in Houston, the VOC morning hours had VOC sensitive chemistry, which transitioned to NOx sensitive chemistry during the daytime. Whereas in San Antonio, using this regression based model, as well as we also did some zero-dimensional Langarian model to analyze ozone sensitive regime. What we saw was throughout the campaign, San Antonio was a NOx limited regime. So what we see in San Antonio is much like what we see everywhere, most of the other cities, bigger cities in the US, whereas unique site is the Houston. Houston's ozone pollution is unique. At Houston, in such morning conditions when we have VOC sensitive ozone production and we have a large amount of industrial emissions producing highly reactive VOCs like isoprene, that favors ozone generation on the following day. And therefore, what we can conclude is that Texas cities have complex emission scenarios, and future efforts to mitigate ozone or particulate pollutions have to consider a variety of emission reduction strategies. Now switching gears a little bit and coming to biomass burning. So the study that I'll show today was intended to evaluate aerosol and gas phase tracers, biomass burning tracers, to identify the in order to identify long-range transported biomass burning emission in an industrial location in Texas, where I'll show some results from Port Aransas. Reiterating again, biomass burning emits a large amount of PM, VOCs, and trace gases into atmosphere, and these biomass burning plumes can be transported across longer distances, impacting downwind air quality. But what is interesting is that during this transport, the physical properties and chemical composition of plumes can be altered significantly due to 2 processes. First is aging process of the plume, and the second is dilution with the boundary layer. So especially in urban locations, it is challenging to characterize and quantify the impact of aged or dilute biomass burning plumes. So this results come of the Corpus Christi and San Antonio field study, which comprised of both mobile measurement and stationary measurement, which is a collaboration between Baylor, Rice, and University of Houston. And in terms of measurements, I had similar aerosol and gas phase measurements in this campaign as well. The specific objectives were to study the physical and chemical properties of transported biomass burning smoke and their impacts on background air quality in Port Aransas, which is a coastal city near Corpus Christi. The second objective was to identify fire source location as well as to understand transport time, aging and dilution of smoke plumes. And the third was to evaluate the challenges of using biomass burning tracers in an anthropogenic area which is already burdened by a lot of local sources. Okay, in this figure, what I show is the aerosol optical properties like AAE and the another aerosol based biomass burning tracer F60, which comes up the AMS measurement, aerosol mass spectrometer measurement. F60 is the fraction of anhydrous sugar in the OA spectrum. So usually F60 greater than 0.3 indicates biomass dominating aerosol. And I also have some other AMS aerosol mass spectrometer based data is later resolved into several factors using positive metric factorization. So I have some results, different factors included in here: black carbon concentration, some CO trace gas, as well as some metallurgical parameters. For the time period of April 9th to 11th, what we see is that we identified two biomass burning events on April 10th and 11th with the enhancement in AAE and F60 value. But what was interesting is that although during both BB1 and BB2 period, there was a clear synoptic peaks or the increment of AAE and F60, as well as some of the general combustion tracers like CO and black carbon, but the patterns were different. We had a very good correlation of these tracers during second biomass burning period, or BB2, but the correlations were poor during BB1. So our hypothesis was that the high variability in this specific biomass burning tracers as well as general combustion tracers during BB1 period was driven by mixed plumes from different sources. Now then, we wanted to understand what are the sources of these biomass burning events. So in this figure, I have overlaid a couple of different things, a couple of different satellite observations and back trajectory analysis. The first thing is the spatial distribution of MODI's satellite-based AOD, or aerosol optical depth, which is a proxy for amount of aerosols in the atmospheric column. The color bar represents the range of AOD. On top of it, I have added a satellite-retrieved VIIRS active fire counts on the orange dots. And the other thing I have overlaid is the NOAA model-based smoke cover. And the last thing, finally, I have 72-hour back trajectory at 3 different heights. So during this time, we saw an extensive fire in central Mexico, Yucatan Peninsula, and central US region. But the difference is that when the biomass burning period started, we had air mass coming off from the central Mexico and Yucatan Peninsula, which over the period of the time during this BB1, it moved towards the northern US, intersecting fires in the central US. Whereas during biomass burning period 2, we had predominantly influence of fires from the central US. So that then corroborates with what we were assuming, that biomass burning had mixed influence of transported biomass burning plumes from central Mexico, Yucatan Peninsula, and central US, whereas biomass burning 2 was influenced predominantly by fires in the central US. And then we went ahead and did some aerosol chemical composition analysis. For the sake of time, I won't go much in detail about this today, but summarizing, we saw some interesting differences between differences in the aerosol composition between when the fires are, when we influence fire predominantly from one source versus 2 different sources. Now, coming to another interesting result, as with the aerosol biomass burning tracers like AAE and F60, they're common or very much used VOC biomass burning tracer. So one of that is acetonitrile. during this BB1 or BB2, we did not see acetonitrile follow the same trend as aerosol tracers. And then that's surprising. So we hypothesized that the acetonitrile in Port Aransas, where our study site was, is impacted by emissions from local onshore and offshore emissions, and some background continental air mass, which was so high that we could not see the influence of biomass burning emission at that time. To determine whether the acetonitrile concentration from biomass burning, acetonitrile associated with biomass burning, would exceed the local background, we did two things. We investigated the geospatial variability of acetonitrile emission using the mobile measurement data, and then we used the regression-based model from the literature to estimate biomass burning associated acetonitrile. When I talk about onshore and offshore emissions in and around our study site, each individual dot here in different colors represent one of the other oil and gas extraction processes going on. Now, when we investigated geospatial variability, what we saw was that these plots show 2 different days of mobile measurement in Corpus Christi region. What we see is that there's a day-to-day variation in acetonitrile, but every time you go around this major industrial corridor in this box, it lights up. So that means that the acetonitrile concentration was clearly enhanced in major industrial sector, and if you get an influence of the air mass from that region, then you're going to get influence of these emissions from industrial sector. And when I estimated the acetonitrile associated biomass burning, what we observed was that our observed and estimated acetonitrile during biomass burning 2 period matched were similar, implying that the biomass burning 2 was whatever acetonitrile that we observed during BB2 period was from the biomass burning plume, transported biomass burning plume. But during BB1, or neither during BB1 or its preceding period when we had continental air mass influence, the observed and estimated acetonitrile did not match. This likely indicates local industrial sources that were dominant at that time. So what this means is acetonitrile cannot be used as a unique biomass burning tracer when there's a big amount of local emissions available in and around that location. And the major question is, what implications would this biomass burning plumes that I discussed have in the Texas air quality, right? So in here, the top plot, I show the Texas state monitoring based ozone data that's recorded during the period. And we see a clear elevation of ozone during both BB1 and BB2 period, which was again corroborated by the aerosol indicator of biomass burning AAE measurement at several different black and brown carbon aerosol optical network in Houston. So therefore, the smoke distribution that was evident in the NOAA's model and the one that we identified in our site possibly had influence in the local air quality in entire southeastern Texas. However, the other important thing is accurately estimating contribution of biomass burning using single point measurements like this is very difficult. From ground-based monitors that federal agencies or state agencies run, they have measurements for criteria pollutants but lack specific biomass burning related measurements. And as the anthropogenic emissions are decreasing and biomass burning emissions are being more interesting or increasing with the changing climate these days, so this study suggested that this study suggested that the state agencies or federal agencies should at least include some low-cost photometers that are available to measure some of the aerosol tracers or indicators for biomass burning. And the other things that we could conclude was aerosol and composition and optical properties are better indicators of biomass burning in an urban location than acetonitrile. With that, I'd like to thank my advisors and mentors at Baylor and all the collaborators who participated during all these field campaigns. Thank you.
have about 15-ish minutes for questions, so if anyone has any, feel free to go ahead. Stand over here. Vikita?
Those high split trajectories confused me a little bit.
Huh?
I couldn't tell how far back, like how long.
These were 72 hours back.
Yeah, these are 72 hours, and they're all from 2 days, April 10 and April 11.
So the starting point, the ending point is, so ending point of the, on this one is 10, on the April 10th was 9 a.m. CST, which was starting time of the biomass burning 1. And the second one was the middle of the biomass burning 1 period.
I just wonder if you don't, I mean, you could also just have smoke that's kind of sloshing around in place.
Oh yeah,
that isn't really.
That's always possible, but it's really difficult to get insights or tell about how vertically or vertically these smokes distributed with the satellite observations.
Might be interesting to just plot out the wind fields and just see what was responsible for this big wind shift.
Yeah, I could try that.
It just seems, I don't know. I guess I'm not totally convinced from this that you have these two distinct smoke sources for what you're measuring in Houston. I'm not saying that you can do it other ways, but you could just have a pool of smoke that's, or I guess Houston's kind of at the edge of your smoke pool. Right,
Yeah,
that's what the yellow is the...
It's the Port Aransas, Corpus Christi. This study was from Corpus Christi. Houston somewhere up in
The AOD, that's the yellow over the Gulf of Mexico?
Yes.
It just looks like Houston is kind of at the edge of maybe this smoke coming off the Yucatan. And
Oh yeah, this
there's,
AOD.
you know, it might just be a land sea breeze or something.
Yeah, Houston.
Anyway, it's interesting, and I liked your talk too. Sorry, I immediately went to the question, but nice talk.
Toby?
So, in the methane to ethane ratio things that you talked about to get the sources, given that methane has a very high atmospheric concentration and very long lifetime, are these ratios, you take the methane above natural background, or how does that work?
We do not take it above natural background. We use the ambient concentration to derive it, but these even methane has several weeks of lifetime, right? And the air masses that were coming off from some of the major sources of oil and gas extraction locations were, if we run the back trajectory, were not even like a couple of hours behind. So all the industrial processes that we were getting influenced from were processed, but not to ace that methane emissions would react out.
Wait, so when you would do these things, I mean, what would be the methane concentration, given the background's about 1.8, 1.9 parts per million, would you see very highly elevated methane levels?
It may be elevated, but would not be, unless you have like a really nearby source or a source that releasing at a very high concentration. So you may not just be able to tell if it's from one specific oil and gas extraction process just by looking at the difference between ambient and background. So, but because ethane emissions are regulated, as well as ethane emissions have different signatures from different sources, so that's why this ethane to methane ratio works out really well in characterizing some of these sources than the absolute concentration or difference with the background.
Cassie?
I had a quick question. So it's interesting that this acetonitrile doesn't work very well as a tracer. But what about the levoglucosan? Like, is that a robust tracer, or is that not that great of a tracer of the biomass burning? Because that's kind of like the atmospheric chemistry standard, but like I saw a bunch of talks at AAAR that were talking about how some of the markers that we use don't work for fires from different locations. Like, they work okay for like North American fires, but not for fuels being burned in other parts of the world. So I'm also curious if like you could comment at all about the use of levoglucosan.
Yeah, so there's been several studies showing degradation of levoglucosan as the blue ages, right? So in our case, it worked. If the F60 or the MOZ60 is totally not levoglucosan, a big part of it is levoglucosan. It worked in our case, but again, there are several places or fires from several sources where the levoglucosan degraded much faster than from some other sources of fire. But what I can tell is if we really want to analyze or have a robust aged or dilute biomass burning tracer, then we'll have to consider finding a unique SOA product or some secondary oxidized, gas phase oxidized products instead of some of these primary pollutants.
Yeah, I just keep wondering, like, because a lot of the AMS analysis is using PMF, right? And so you can use the levoglucosan and or the acetonitrile, and if neither one of those work, it kind of makes me wonder how much of the SOA is actually really smoke.
Yeah, so
you just don't know it.
Yeah, true. And then in our case, when I analyzed the PMF from the AMS data, so the BBOA factor and more oxidized OA factor, when we summed up these two factors, then we could see a good trend of biomass burning influence at that time. So obviously it's really not possible to have these kind of high-tech instruments run over the year.
Right.
So these measurements always come of some opportunistic field campaigns, right? But PMF factors were really beneficial, or were able to identify biomass burning fluids.
Thank you.
Any more questions? Great, let's thank Sujan again for a wonderful talk. Quick announcement, the Compass talk on Friday will start 10 minutes early at 10:50 a.m. because we have 4 speakers. And then next Wednesday's Compass talk will be in the auditorium, not this room. So I'll hope to see you all Friday.